Hey everyone, this is Jason Dinsmore from organicchemistoncall.com. What I wanted to do is talk about today just a very simple topic where we're trying to figure out how many bonds can we have to each atom and what would it look like. So in general chemistry, you essentially talk about the entire periodic table, everything that you see here. What's nice about organic chemistry is we can essentially, it's obviously going to be more than what I'm showing you here, but I'm going to try to get just a general idea here. So we'll get rid of all of that, this, and that might be pretty good. These are really all the elements that you're going to, actually we can even just delete these because these aren't really important here. So we can get rid of that, delete all that. So this is really kind of the atoms that we really have to concern ourselves with. So what I want to show you here is that you can use the periodic table to kind of give you a feel for, or to show you rather, how many bonds you can have to each atom, just in case if you're going through and doing mechanisms or reactions and you kind of sometimes might get confused. So if we look at this, what's nice about this is if we go to our inert gases, we see these numbers up here. We have 3, 4, 5, 6, 7. Inert gases would obviously be 8. What's nice about this is this allows you to know how many electrons are around the atom. So let's just take fluorine, for example. So if we take fluorine, what that says is we should have a total of 7 electrons around there, and we know that each should have a pair of electrons if we can. So that's 2, 4, 6, and then anything left over is 1 by itself. So that's going to be fluorine. If we just flip over and go to oxygen, that's going to have 6. So we can do 1, 2, 3, 4. And now what we would think about here is we would go 5, 6, and everything's paired. Now what happens from, I'm just going to put, let's see here, we'll put inert gas so we can kind of see some trend here. 1, 2, 3, 4, 5, 6, 7, 8. All right, and we'll move this over here. We'll bring this a little closer. Okay, so if we start from inert gas, everything is filled. And then you'll notice as we go to 7, we pluck one of those off. And then when we go to 6, we don't bring all the electrons to make sure that they're all paired. We're consistently just plucking one off at a time. So if we pluck one off from that position, then we can pluck one off from that position. And you can see where we're going here. So the nitrogen is going to look like that. And then when we eventually get to carbon, we're just going to have 4 electrons around it. So how does this help us? Well, anytime you see a single electron, that's going to tell you how many bonds you can have to each atom. So fluorine can only have 1 bond. Noble gases or inert gases can't have any. Oxygen can have 2 bonds. Nitrogen can have 3 bonds. And carbon can have 4 bonds. Now specifically what this one way, because some of these can actually have more bonds than what are shown here, what it tells you is that if fluorine has 1 bond, it's neutral. If oxygen has 2 bonds, it's neutral. If nitrogen has 3 bonds, it's neutral. And if carbon has 4 bonds, it's neutral. So that's just a really quick way of doing that. So now that we've got this drawn out, let's shrink this, and let's take a look at different ways of doing this. So there's obviously only one way that we can do a fluorine bond, but oxygen is really kind of the unique one and the odd one that we can think about. So if we take oxygen, and we'll just go ahead and put our 2 electrons, well, we can leave it similar to what we've got, 2 electrons like that. So we could have 2 bonds. We could have, we'll just make this simple, a CH3 and a CH3, or those could be hydrogen, so you could have water, or that's an ether. The bonds don't have to be separated like that, so if we wanted to, we could take an oxygen and we could scoot those 2 electrons over there, those 2 electrons over there, and if we bring those lines down, we can actually have 2 bonds to a single atom. I'll just put R, R. So we can have 2, we notice that we still have 2 bonds, but instead of having 2 single bonds, we have 1 double bond, or kind of 2 single bonds in the same area. The only other one that we can do is instead of having an oxygen with 2 separate bonds, we could actually take this system that we initially saw and we could form a ring out of it. So it doesn't have to be acyclic, it could be cyclic. So we could do a cyclic system. So oxygen is kind of the oddball out where we're always going to have 2 bonds, but they don't necessarily have to be 2 separate bonds. They can be squeezed together or they can be cyclical. I guess now that I brought that up, we could also look at nitrogen. So if we look at nitrogen, the typical way that we see that is it's going to have 3 bonds like this. But with nitrogen, we could also take those electrons, just like oxygen, and we can bring 2 of them down, and we can have, oops, and there's still going to be a hydrogen up here. We still have our 3 bonds, but now what we've got is we have 2 of those bonds squished together, and you can see where this is going. We can probably squish 1 more down. So if we had all 3 down like this, just put R, we can do that as well. So with oxygen, although we have two places to bond, we can squish those two together or break them apart, and with nitrogen we have three. We can either keep them separate or slowly one by one squish them together, where we go from all single bonds to a double bond and a single bond to a triple bond. And then carbon, if we look at that atom, so we have carbon. So carbon, the typical way that we see it is it has 4 bonds, or the way that you first are introduced to it, something like this. You can do the same thing, so I guess I shouldn't have put, well, it doesn't matter. We could take 2 of those, and we could squish another one down. It's a real technical term, squish, if you're wondering. We could have 3. However, what we are not going to see is 1, 2, 3, 4, like that. That is no good. So the maximum amount that we can squish down, if we look at nitrogen carbon, is 3.